Okay, good afternoon, everyone. Last class, we started off with mathematical modeling involved in control system engineering. And we discussed why mathematical modeling is done and how it is going to be useful for analysis of a given system and prediction of behavior of a given system. As we discussed in the last class, while preparing a mathematical model for a given physical system, when I say physical system, let it be a mechanical system, let it be electrical system, let it be hydraulic system, let it be pneumatic system. Machine tool control system. So whatever systems are physical systems are available, all those systems can be mathematically modeled for predicting their dynamic behavior. Now, what do you mean by dynamic behavior? When such systems are subjected to dynamic inputs, when I subject them to impulsive input, when I subject them to step type of input, when I subject them to ramp type of input, when I subject them to sinusoidal type of input, how they are going to behave. And all these things we'll be doing on paper. We'll be building a mathematical model first. How these mathematical models are built, by understanding first of all the functional behavior of a given system. How is its functionality, and thereafter studying each element, functional element in a given system, we try to identify what are the physical principles involved in their functionality. Uh, as we discussed in the last class, we make use of Newton's laws of motion. We make use of Kirchhoff's laws, Kirchhoff's current law, Kirchhoff's voltage law. We make use of laws of conservation of mass, law of conservation of momentum, and law of conservation of energy. So whatever physical laws we have studied, and some thermodynamic laws even. So whatever basic laws we have studied related to such physical systems, we make use of those laws, try to correlate the functionality of a given system and element with the physical law concerned. And then once we identify the physical law concerned by making use of the principles of involved in that physical law. Now, what is that physical law? Newton's laws of motion, Newton's law of motion, Newton's second law of motion, Newton's third law of motion. Now, this particular system is behaving based on action-reaction principle. Then we have to make use of Newton's third law of motion. Now, while analyzing an electrical system, electrical circuit, so to say, we can make use of Kirchhoff's current law, Kirchhoff's voltage law. Similarly, even in the flow-through pipes, flow-through turbines, when we have a flow system, either we make use of Bernoulli's equation, we make use of laws of conservation of mass, momentum, and energy. We make use of other physical laws, even laws of friction we make use of. Some laws of mechanics we make use of, and we try to identify which law is connected with the behavior of this fluid system. Suppose I am talking about a paintbrush. As we all know, the paintbrush, when we immerse that paintbrush in the oil paint, it is it has got more flowability initially, isn't it? When I just put that brush inside and then take a paint out of it, and then I start painting a surface, what happens is initially the brush runs very smoothly, and slowly over a period of time, it becomes tougher for us to move the brush, isn't it? We feel that it is because of drying. Yes, to some extent it is because of drying, but basically the physical law that is concerned here is the law of viscosity. Now, what is this law of viscosity in this case of paintbrush? So what it means to say is the viscosity in this case of oil paint, the viscosity of this oil paint is time dependent. Initially its viscosity is high, right? And thereafter it becomes thicker. It becomes thicker. It becomes difficult for me to move the brush. Okay, so it is a law related to viscosity. So Newton's law of viscosity, I need to make use of. What is that Newton's law of viscosity then? Shear stress tau is equal to mu into dou u by dou y. If you remember, so velocity gradient. So mu is the coefficient of dynamic viscosity into velocity gradient dv by dy or dou v by dou y, right? So what happens here when I'm moving the brush? What I'm experiencing is it becomes difficult for me to move the brush. What does it exactly mean? I've got paint on the surface, right? On the surface. So whatever thickness it has got, that is a fluidic layer. And what I'm trying to do, I'm just moving the brush over that paint, isn't it? So what I'm doing actually I'm applying one tangential force on the paint surface. So what I'm doing exactly, I'm applying some shear stress over that paint layer, right? So this shear stress tau is proportional to velocity gradient, and its constant of proportionality is mu, that is coefficient of dynamic viscosity. So this mu, which will be, if I solve this tau is equal to mu into dou u by dou y. If I solve it for mu, what I'll get? Mu will be equal to tau upon dou v by dou y or dou u by dou y, whatever nomenclature we make use of. Basically what it is, mu, coefficient of dynamic viscosity, isn't it, is equal to shear stress upon velocity gradient. Now when I say that this mu is changing with respect to time, what does it mean? Mu is maybe increasing. So what is happening? Mu is equal to tau upon dou u by dou y. So when mu is increasing, tau will increase. So the resistive shear stress that I am applying, I need to develop more shear stress. So I need to apply more tangential force. And this is how we have to correlate this physical phenomena or physical phenomenon with the law that governs that phenomenon, isn't it? So in this case, in the case of paintbrush, if I'm asked to develop a dynamic equation for this paint brush or painting activity, then I need to make use of Newton's law of viscosity, which is tau is equal to mu into dou u by dou y. This just as an example, every physical system, every dynamic physical system. Now, what do you mean a dynamic? The parameters which are changing with respect to time are dynamic system, isn't it? And here in the dynamic system, forces are involved, motions are involved, and basically these parameters, dynamic parameters, are changing with respect to time. Now, what are the kinematics then? Kinematic parameters. The parameters are changing, but those are changing. What are the changing parameters in kinematics? Changing parameters are displacement, velocity, acceleration. Force is not involved in kinematics. Whereas in dynamics, the motions, displacement, velocities, accelerations, and the causative forces. Force is also involved in dynamics. So I need to make use of kinematic equations. I need to make use of dynamic equations which govern that physical phenomena. Okay. So while doing so, as we discussed in the last class, it is not always possible to develop a perfect model. If I try to make a more realistic, understand the physical phenomena and every parameter, every aspect of it, if I try to model, my equation describing the dynamics of that system becomes very complicated and complex. Our objective is not to build a complicated mathematical model. Our objective is to build a model which is easy to solve, which captures every aspect of that physical system, right? Very important aspects of that physical system. And it also serves the purpose for which I am carrying out this dynamic analysis. म्हणजे काय, जसं सस्पेन्शन सिस्टमचं आपण फॅमिलियर एक्झाम्पल घेतलं, मी फक्त मला बाकीच्या सगळ्या डिटेल्स मध्ये आय एम नॉट मच इंटरेस्टेड. व्हॉट आय एम इंटरेस्टेड इज आय एम लुकिंग फॉर अ गुड सस्पेन्शन सिस्टम डिझाईन. आणि त्यात काय अपेक्षित आहे, खड्ड्यातनं गेली किंवा स्पीड ब्रेकरवरनं गेली तर द रायडर ऑर द ऑक्युपंट शुड नॉट फील द पिंच. माझ्या बटक्सला पिंच व्हायला नाही पाहिजे, मला त्रास नाही व्हायला पाहिजे, मी उडला नाही झाला पाहिजे. म्हणजे काय? The force transmitted to the rider should be minimum is my major objective, and the displacement transmitted to the rider should be minimum. This is how I have to describe the objectives of my study first, and then based on my objectives I should build the mathematical model, which is maybe to some extent simplified even, though it is not highly realistic, but it captures the dynamic aspects of that physical system, and it serves my purpose of predicting this behavior. It serves my purpose of designing a good physical system. Okay, this is what we discussed in the last class. Let us move further. Now, in mechanical system, in our curriculum, we are supposed to study, because physical mechanical systems are there, electrical systems are there, electronic systems are there, computer systems are there, geographical systems are there, climate control systems are there, demographic systems are there. Every system can be modeled. Even fluid systems are there, hydraulic systems are there, pneumatic systems are there. Out of that, as per the specifications or the details given in the syllabus, we are supposed to study the mechanical system. That's what they have written. We'll try to cover some other systems also if time permits. So in mechanical systems, we'll be basically studying translational mechanical systems and rotational mechanical systems. Now, what are these translational mechanical systems? So I'll be considering the linear motions, right? Linear motions are the translational motions, which are defined in terms of x, y, and z coordinates. I'm not bothered about the rotational aspect of it. I'm just measuring the linear or translational aspects of mechanical systems. So this is one part of study. And secondly, I'll be studying the rotational mechanical systems also. Now, any translational mechanical system, I'm using the word any translational mechanism. So any translational mechanism, when I say, let it be a robo base, let us say, the robo carrier. The robo moves in X direction, the robo moves in Y direction, the robo moves in Z direction. Wherever linear motions are involved, I'll be making use of the principles of translational mechanical system analysis. Wherever I have a translational motion. Now take the same case of a robot when there is a gripper which is gripping the job. Now that grip job is rotated also, isn't it? So this gripping motion is translational motion, whereas this rotation motion is rotational mechanical system, isn't it? So I make use of rotational mechanical system analysis concept when I'm designing a gripper. And there are specifically rotational elements also. When you have a fan, ceiling fan in your room, there's a shaft. On that shaft, the rotor is mounted, and then that shaft is subjected to torsion, let us say, or rotational motion. So the rotating shafts, wherever those are involved, in a machine tool it is involved, in a motor it is involved. So various physical systems will find rotational motion involved. So all those rotational components can be modeled by using rotational mechanical systems analysis. And all the translational mechanical system concepts can be used for modeling all the physical systems which are subjected to translational motion. Now, if you're talking about translational mechanical elements, now these translational mechanical elements, I cannot have the representative model for each and every component. What I do is, I generalized. I study various translational mechanical systems. And what I observe is that the behavior of that translational mechanical system can be captured, can be modeled by using three basic elements. So every translational mechanical system, basically it will have some inertia component. When it is in motion, right? What Newton's first law says, the inertia concept, it says the product or the object continues to stay in the state of rest or continues to stay in the state of motion as long as it is acted upon by some external force, right? Once that force is removed, still it keeps on moving. What is the reason? Because of the inertia force. Or suddenly I apply the brakes. I am moving in a vehicle, I am moving in a bus, I am moving in a car. It is moving at 40 kilometers per hour, and suddenly I apply brakes. So what is happening here? I am sitting inside a car. The car is on the road. The car is moving. So car is moving at 40 kilometers per hour with respect to ground, isn't it? Ground is stationary. So I am sitting inside a car. Now, because I am inside a car, I am also moving at 40 kilometers per hour. Now, when I suddenly apply brakes, even though I apply the brakes, what practically happens is the vehicle, I'm trying to stop the vehicle, or I want to reduce the motion of the vehicle by applying brakes. With respect to what? With respect to ground. So vehicle tends to stop with respect to ground, right? And what is happening to me? The vehicle is not stopping me unless until I am belted tightly to the vehicle, unless or until I become part of that vehicle. Otherwise, if I am not having any seat belt connected, I am free to move forward, backward. Even if the vehicle is moving forward, I can move back, isn't it? So there is a relative motion between me and the vehicle. But the vehicle has got relative motion forward or backward with respect to ground. So what happens? When I apply brakes, the vehicle tends to stop, or vehicle tends to decelerate with respect to ground, right? But I am in the state of motion. What happens when the vehicle is stopping, right? I tend to move forward, isn't it? आपण आपटतो पुढे. बऱ्याच वेळा एसटी मध्ये झोप लागली की डोकं आपटतं आपल्या समोरच्या बार ब्रेक लागला एसटीचा. What is the reason? Because the inertia, my inertia plays a major role there. So I tend to keep on moving forward. The vehicle is stopping, isn't it? So this is the inertia effect. So like this, every translational mechanical system will have inertia characteristics. Now these inertia characteristics are dependent on what? Basically those are dependent on mass, isn't it? And the action of external forces and the velocities and accelerations involved later on, basically. So masses, so any translational system will have the inertia effect if they have got masses. So what they have done, the researchers, they identified for modeling a translational mechanical system, mass is required. So mass in any form, the vehicle mass and the rider mass, isn't it? So like that, every translational mechanical system will have some mass that represent the inertia or resistance to, what is inertia? Inertia is resistance to acceleration. In the case of a car, the car is trying to decelerate, but I keep on accelerating along with the vehicle, isn't it? That's why the inertia comes into play. So every translational mechanical system will have inertia component. Then every translational mechanical system will also have spring or spring-like element, right? Spring, exactly, if I'm talking about suspension system, okay, so a spring physically will be there, right, in a suspension system. But what is the characteristics of that spring? The motion, if it is hung, if I'm applying some external force to that spring, what it tries to resist that motion, isn't it? And that applied force and the resistance to the motion. What is this resistance? When I apply external force F, the spring will react to this external force. The spring will have its own reactive spring force, isn't it? Which will try to resist this motion, isn't it? So spring force will be proportional to, or the displacement of the spring will be proportional to spring force, right? And this constant of proportionality is stiffness of the spring, isn't it? If I'm talking about a linear spring. So F is equal to stiffness K into X, because spring force F is proportional to displacement X, or displacement X is proportional to spring force F, and the constant of proportionality is stiffness K, isn't it? So F is equal to Kx is the equation of the spring. So this is about actual spring. We are talking about all the translational mechanical systems. So everywhere spring might not be there, but spring-like behaviors will be there. What do you mean by spring-like behavior? Any shaft which is resisting that motion, any shaft, any bar, I am applying some tangential force, it tries to come back to its original position, isn't it? So this is also stiffness property, not necessarily spring. Spring is पाहिजे असं नाही, but springचं behavior काय? It is related to stiffness of that spring. तसंच any translational mechanical component will exhibit some stiffness like property or spring like property. जिथं जिथं स्टिफनेस लाईक प्रॉपर्टी मला दिसेल, एक लिव्हर आहे, त्या लिव्हरला फलक्रम आहे आणि आय एम अप्लाइंग सम एक्सटर्नल फोर्स ऑन दॅट लिव्हर. तो फोर्स रिमूव्ह केला तर काय होतं, तो बार जो आहे लिव्हर आहे, इट ट्राइज टू स्ट्रेटन अप, हो की नाही? स्ट्रेटन अप व्हायचा प्रयत्न करतो, म्हणजे काय? बिकॉज ऑफ व्हॉट इट ट्राइज टू स्ट्रेटन अप? बिकॉज ऑफ द स्टिफनेस ऑफ द स्प्रिंग, isn't it? It is related, the deflection is dependent upon the stiffness of that bar, isn't it? So though it is spring, exactly spring is not there, but spring-like behavior is there. So what the researchers thought, apart from masses, the physical systems will tend to show this spring-like behavior. So I can make use of spring as a representative element for depicting, for showing the stiffness property or spring-like property. In suspension system, as I said, there will be proper ring, proper spring. But in other systems, I can model it with the help of a spring. Spring म्हणजे काय? Spring एक helical spring मी coil दाखवतो. But what I'm interested in is stiffness property मध्ये मला interest आहे. Remember, we are talking about mathematical model. हे modeling करत असताना any of the translational mechanical systems can be modeled by using three basic elements. कुठले कुठले? मास और मास लाइक एलिमेंट. मास म्हणजे वजनच पाहिजे असं नाही, प्रत्येक बॉडीला माझं स्वतःचं वजन आहे, तुमचं स्वतःचं वजन आहे. So it has got some mass, isn't it? So any translational mechanical system will essentially have the inertia like elements or mass like elements. Secondly, every translational mechanical system will have stiffness property or spring like property. So I can model translational mechanical system 1 by using masses, by showing a representative mass, by showing representative spring. Remember, mass corresponds to inertia property of that translational mechanical system. Second, spring corresponds to not necessarily spring only. If physically spring is there, spring I'll be modeling. But if spring physically is not there, but it has got stiffness like property, that also I'll be modeling by using a spring in my a free body diagram, by showing the behavior of a physical system. Functional diagram, if I try to draw, I show the functional diagram, I draw the functional diagram by making use of a spring symbol. But does that mean that physical system will always have spring? Not necessarily. It will have spring-like elements. It will show spring-like property, right? So secondly, any translation mechanical system can be modeled by using springs. Third important translation mechanical element that we are going to consider is dashpot. In a suspension system, dashpot आपण shock absorber म्हणतो की नाही, fluid filled dashpot. What it does, the damping force is proportional to velocity of motion, isn't it? So the damping force Fd is proportional to velocity, or dx by dt, right? In operator term, dx, capital D, small x, it is proportional to velocity. And the constant of proportionality is damping coefficient or damping factor. Now that we normally represent it either by B, capital B, or by using capital C. It's a matter of nomenclature. So basically, now what do I mean by this? I'll be able to model a translational mechanical system only if a shock absorber is there? Not necessarily. In a suspension system, a shock absorber damper will be there. That I'll be modeling by using a damper proper, right? Or I will try to identify what is the damper property. It damps the motion. It damps, it reduces the motion. Now, if I don't, in a translational mechanical system, if I don't have any damper, but I have lubricated elements, right? The lubricated joints. Now they are also damping the motion. So even though the dashpot or damper is physically not there, but that lubricating oil is doing the same work. It is doing the damping work. So that lubricated joint can be modeled by using a dashpot, isn't it? I can always have a dashpot proper in a given system, but in some systems there will not be dashpot proper, but dashpot like behavior will be there, right? The lubricated parts, right? Particularly grease lubricated part, oil lubricated part, they're damping the frictional motion, they're damping the motion, so they are dashpot like elements. So in a nutshell, any translational mechanical system can be modeled by using three basic elements: mass, spring, dashpot, or spring, dashpot, mass, whatever is the sequence. So these three basic elements will be sufficient to model any of the translational mechanical systems. Remember, any of the translational mechanical systems. So this is how the researchers came out with the concepts of mathematical modeling of translational mechanical system by using these basic elements. The mechanical systems does not have to be really made up of springs, dashpot and masses, but have the properties of stiffness, have the properties of damping, and have the properties of inertia. Even in that case, I'll be modeling such systems by using spring, mass, dashpot, isn't it? All these building blocks can be considered to have force as an input and displacement as an output. In case of these translational mechanical systems, I'll be using force as the input and displacement as the output. I think, friends, we'll stop for today.